Mankind has dreamed of spying into secrets of the universe since the beginning of time. These dreams became more real since the later part of the 20th century. The Hubble telescope, a joint project of NASA and the European Space Agency, was placed into Earth's orbit in April 1990, where it is still operating today. It was designed to observe space objects within visible range and near ultraviolet range. For 20 years working in the orbit of the Earth, the Hubble obtained more than 1 million various images of stars, nebula, galaxies, and planets. Thanks to this space observatory, the maps of Pluto and Uranus, dwarf planets of the solar system, were formed. Ultraviolet polar glows were for the first time observed on Saturn, Jupiter, and Ganymede, a satellite of Jupiter. Scientists were able to confirm that the hypothesis proposing that the majority of the stars in a galaxy have planets in the process of formation. These are just a few achievements of this unique scientific instrument. However, and unfortunately, immediately after its placement into orbit, a serious problem was detected in the construction of the telescope, a defect of the primary mirror. In order to correct the defect, a list of expensive measures were taken, thus leading to a sufficient increase in the project cost. The telescope was visited by specially equipped missions of reusable space shuttles 4 times. During each of these missions, the astronauts walked in space several times to repair and replace the defective equipment. The Space Shuttle program formally ended August 31, 2011. After its end, the possibility to serve the Hubble telescope ended as well. Although the Hubble will work as a minimum until 2014, it's obvious that a replacement will be required. It was decided to design and fire into space a more modern and powerful telescope. This orbital infrared observatory was first named the Next Generation Space Telescope. The Next Generation Space Telescope is the child of NASA, European Space Agency, and altogether 17 countries, which take part in the project. It was renamed in 2002 after NASA's second administrator in the 1960s, James Edwin Webb. This space observatory is supposed to be the largest scientific space station ever launched into space. This telescope was called the James Webb Space Telescope. Specialists worked on the designing of the new telescope because it was planned to be not only better than the Hubble, but better than all existing Earth-based and space observatories as well. The essential decision was to launch the James Webb Space Telescope as soon as it was ready and pass all the prescribed tests in the year 2000. Initially, NASA management insisted on the mirror diameter to be 8 meters, 26 feet, but in 2002, there were changes in the project, and the diameter decreased to 6.5 meters, 21 feet. The scientists also decided to use an innovative solar shield, the size of a tennis court. To the year 2005, all basic characteristics of the telescope's weight and diameter were determined. Weight, 6.2 tons, 14,000 pounds. Mirror diameter, 6.5 meters, 21 feet. The total area of the mirror collecting surface, about 25 square meters, 270 square feet. Focal length, 131.4 meters, 431 square feet. Astronomers have also determined the point of space where the James Webb Space Telescope will make observations more efficiently. The new telescope was demonstrated to the public at the World Science Festival in June 2010. Besides some of the miniature copies, a full-size model of the James Webb Space Telescope was constructed in Battery Park. It left a lasting impression on the festival guests. However, in June 2011, unpleasant news was reported, saying that the cost of the project already had exceeded the primary calculations by at least 4 times. It was planned that the telescope would cost taxpayers $1.6 billion and would be launched in 2011. However, by new evaluations of specialists, the cost of the telescope may reach $7 billion. At the same time, it would be launched not earlier than 2018. A suggestion to terminate the project financing in full was made by the U.S. Congress during a discussion of the budget for 2011. Finally, after long discussions, the budget was revised, and the project called James Webb Space Telescope had kept its state support. The main element of the telescope is its mirror. The first stage of the mirror's birth was the preparation of beryllium. A geological excavation of rock containing great amounts of beryllium minerals was performed in the desert of Utah. By means of various technological processes, they obtained the beryllium metal, having, by the way, a very high cost. One of its major advantages is that it has a very high elasticity modulus, more than any other steel. This feature is important if the telescope works in conditions of change, with extremely low temperatures to extremely high temperatures. A reflector behind the mirror was produced from beryllium and followed through stages with mirror surfacing and polishing. During these stages, the reflecting segments of the telescope were molded into necessary shapes. All measurements were made to the nanometers, and the work began again. These requirements for accuracy are important because the James Webb Space Telescope needs to work in conditions of exclusively low temperatures. Its working temperature will be minus 240 degrees Celsius or minus 400 degrees Fahrenheit. In such aggressive conditions, it is necessary to get the maximum performance from the working equipment and use any possibility to improve the image quality. The process segments of the craft are gold-coated to make them automatically respondent to any intensity changes of the project being under observation. It is proposed that the telescope's mirror will be able to catch light from the nearest and the farthest galaxies of the universe. Let's recall the diameter of the Hubble telescope's mirror is equal to 2.4 meters, 7 feet, with a reflector collecting area of 4.3 square meters, 48 square feet. And the primary mirror of the James Webb Space Telescope has a diameter of 6.5 meters, 21 feet, with the collecting area of the reflector coming to 25 square meters, 270 square feet. Altogether, it is 5.5 times larger than the Hubble. These sizes are too large for contemporary launch vehicles, and that's why the mirror on the James Webb Space Telescope was composed of 18 hexagonal segments, which will unfold after the telescope is launched into outer space. The correct mutual position of each of the 18 reflectors of the telescope's primary mirror is one of the most necessary conditions for successive work of the entire scientific station. The primary mirror focuses on the image of receiving set, and it is unacceptable if at least one of the segments is in the wrong position. However, it was supposed that in icy conditions of the outer space primary mirror, defocusing will happen anyway because the reflecting segments will change their position. For this purpose, a system of drivers and micro-engines were invented so that the telescope will be able to perform once during a few days of automatic calibration of the reflectors positioning themselves in order to gain the ideal focus. In order to get high-quality images, besides perfect focusing of the mirrors and the possibility to aim the entire system to the target, it's necessary to provide a permanent temperature of all the telescope's systems. This task can be achieved by the application of a solar shield, which will automatically unfold as soon as the telescope reaches its operating point in space. This shield will protect it from the sun's heat and light. The shield is composed of 5 layers of superfine polymade membrane called Captain E. Each layer is covered with sprayed silica and aluminum, which is applied to the surface by an evaporation deposition method. The external membrane is 0.05 millimeters and will reflect 80% of solar radiation. The consequent layers will be thinner and will continue to decrease intensity of the heat flow. Besides protecting it from the heat, this shield will also be a defense from possible micrometeorites. It is expected that if a micrometeorite pierces the first layer, the James Webb Telescope will lose its momentum and blow up in 1 second. If by any reason this shield fails to unfold, the whole mission will definitely fail. The carrying frame, or to say more correctly, the backplane, is produced of composite materials, which is the main element of the telescope construction. It holds all the general details, including 18 segments of the primary mirror. The main requirement to the carrying frame is its low coefficient thermal expansion. If the carrying frame, under the influence of temperature, drops or changes its geometry, this will lead to the changing of the mutual position of the optical system details, which will surely influence the quality of received images. The acceptable changes in the frame geometry are between 40 and 50 nanometers. An automatic refocusing of the reflector elements will be enough to compensate for the errors which will follow such changes. The James Webb Space Telescope will have 4 scientific instruments. The first and the main is the instrument to obtain images in average infrared band, which was developed by the European Space Agency and the NASA Rocket Propulsion Laboratory. It will use 3 photomasks operating at -270 degrees Celsius or -454 degrees Fahrenheit, which will require applying an active cooling system. The second scientific instrument is a spectrograph with an infrared band, which was designed by the specialists of the European Space Agency in cooperation with world-known optical company Carl Zeiss. The third device is a camera with an infrared band designed by the University of Arizona. The last and the fourth instrument, which targets and pinpoints navigation, is manufactured at the Canadian Space Agency. The last 3 devices will not have any active cooling system, because the cold in space is expected to be -240 degrees Celsius or -400 degrees Fahrenheit, and this will provide a normal operation. The scientists have taken a principled decision that the James Webb Space Telescope will not have the possibility to receive images in the visible spectrum. The colorful pictures which, for example, were made by the Hubble are not necessary for scientific research and contain much less information. However, the less spectacular but more informative for the astronomers are the photographs made in infrared band. Using the infrared band, it is not visible to man's eye and not possible to use it from Earth's atmosphere. That's why the best operation place for the James Webb Space Telescope is outer space. On the Wings of Apollo is the name of the set of tests applied to the James Webb Space Telescope. This name is used because the application of these tests, the space environment simulation chambers, were initially built to work with the spacecrafts of the Apollo series. Today, after a few modifications, they became applicable for the testing of the James Webb Space Telescope. During testing, the space vehicle is cooled to extremely low temperatures in circumstances where the air pressure is almost non-existent, which allows simulation of the outer space conditions as if it were actually in outer space. The tests, in order to clarify how the space vehicle will behave in conditions of exclusively low temperatures, are called cryotesting. Besides cryotesting, one of the most important tests is to make clear how the telescope will survive load factors and vibrations during vehicle launch and takeoff. It's easy to guess that the very initial stage of the telescope's mission will be the most difficult and dangerous. Therefore, the mirrors and other elements of the optical system, subtle mechanisms, drivers of reflecting segments, infrared detectors and cameras, must retain their workability during several minutes of extreme vibration, which unavoidably goes along with the vehicle launch and takeoff. Lots of tests are repeated several times, both for separate elements and devices of the telescope and the entire construction. The James Webb Space Telescope must take in stride everything that is assigned to it by the test engineers in order to bear the name of the most powerful telescope in the world. The main task of the James Webb Space Telescope is searching and obtaining of images, stars, and galaxies, which were primarily formed after the birth of the universe, that is, after the Big Bang. This information will help scientists to understand better the formation process of stars, planetary systems, and galaxies. The data received by the telescope will be used to simulate the universe evolution. We will be able to see what our universe looked like almost 14 billion years ago, and to follow up with all its development stages. There is one more question attracting astronomers. It's the process of the collision and merger of the galaxies. In result of the interaction of their gravity fields, they collide, forming new and larger galaxies. The spiral branches of the Milky Way show that it was formed in a collision like this. The majority of elliptic galaxies being observed today were formed in result of collisions which took place billions of years ago. The James Webb Space Telescope will probe the earliest periods of our galaxy formation by looking deep into space to see the first galaxies that formed in the universe, only a few 100 million years after the Big Bang. This will help to confirm or explode the theory stating that in the nearest few billion years, the disk-like galaxies, Milky Way, and its bigger neighbor Andromeda will merge into one big elliptic galaxy. The James Webb Space Telescope will help to determine physical and chemical parameters of the planets and planetary systems located far from us. It will be able to detect relatively small planets, which are only a few times bigger than the Earth. For the first time, scientists will be able to obtain a visual confirmation of the things they previously could see only in their calculations. That is, images of planets in orbits of other stars will be available. Specialists will be able to analyze the conditions on the surface and atmospheric composition of these planets. Visualization of planetary systems formation will help to understand how currents of dust and gas eddy formed our native solar system. Why did some of the planets become gas giants and others became big pieces of stone? And finally, how was the Earth born with such a diversity of life? The telescope will be able to see what happens inside thick clouds of planetary systems being formed deep in space. The launch of the James Webb Space Telescope into space will be performed by the European Heavy Launch Vehicle Ariane 5 from the spaceport Kourou, situated in France, Guyana. It will be launched not earlier than 2018, in contradiction to the Hubble telescope that is operating at low Earth orbit at an altitude of 569 kilometers or 353 miles. The James Webb Space Telescope will be placed in the Sun-Earth L2 Lagrangian point at a distance of 1,500,000 kilometers, or 930,000 miles from Earth. The journey to this point will take 3 months. The L2 Lagrangian point is an ideal place for orbital space observatories. Actually, the telescope will stay behind the Earth orbit, in the Sun-Earth line. Staying in this place will provide the telescope with the highest gravitational stability and best view. At this point, the solar shield will work most effectively as far as keeping the telescope protected from the light of the Sun, Earth, and Moon, which is very important in order to provide a required permanent low-temperature regime. Another advantage of the L2 Lagrangian point is that an opportunity to see meteorites the kind of sizes that are able to deactivate or damage the telescope's elements is virtually possible. The James Webb Space Telescope will move round the Sun as far as it will be under the gravitational pull of the Sun. Its orbital rotation period will be equal to the Earth's period, i.e., during 1 year, the telescope will complete 1 rotation around the Sun. The mission of the James Webb Space Telescope will not take less than 5 years. As the distance to the L2 Lagrangian point is 4 times larger than the distance between Earth and Moon, the service of the telescope will be sufficiently more expensive and difficult than that of similar operations performed by the Hubble. However, these tasks are planned by the sending of special robots to the telescope, along with sending space repairmen on a multi-purpose aircraft. Orion, which has been being developed by NASA since the middle of the 2000s, is not excluded. Scientists look forward to the moment when the James Webb Space Telescope proceeds to its work. We hope that its launch and space journey will be free from emergency situations, and it will not disappoint us during its operation as it was with the Hubble. We hope that the results of its work will indeed draw us nearer to the disclosure of the universe secrets. We hope mankind strives to do that throughout history.